All right, picking back up where we left off. Remember, last time we did this, it was a quick review going over it. This time you're responsible for it. So we are going to cover this. And it's on your test. All right, voltage varies with position as far as where the wires, or I should say the armature, is in relation to the magnets. Now, I don't know if you can see it real well up on the screen, but we have a north and a south magnet. They're permanent magnets in this particular scenario. There's no electricity in these magnets. They're not electromagnets. They're just magnets. And you can see the lines of flux represented here. They're all concentrated right here in the north and the south. And as you get towards the ends, they sort of dissipate. So the lines of flux are the strongest right there in the middle of the magnet. So what did I write? The greatest voltage occurs as a conductor passes right angles to the flux. So in this particular case, this armature is swinging around. You can see I got the south is going up and this side on the north is coming down. So they would obviously be in this general area right here. I think the next slide better have that right. These should actually be moved in to right here, but I got it out there. So as this particular armature is going up in this position, this one is going down in this position, you can see they're cutting through those lines of flux, and that's a good keyword for you. They're cutting through the lines of flux. So if the wires are cutting through the line of flux, what is being induced into the wire? Voltage, current, power. All right, but as it moves around, because it's a circle and it comes, and now suddenly we've got one wire of the armature is going from the south to the north, and the other one's going north to the south, but they're on the outer edge, number one, where there's not a lot of flux. Number two, it's going parallel to the line of flux. So if I got a magnet in a wire and I'm going parallel, if I got a magnet here and a magnet here, and I go this way between the magnets with the wire, I get nothing. It's not cutting through. It is going along with. You got to go against the grain here to get some power going. So you're going to get, like what? Like friction? Sure, yeah. So you're going to get nothing here. So when we're doing this, we're going to get nothing. Now this is where we come back to the current flow, the left-hand rule. Remember, we had the thumb points in direction of rotation. Finger's the field, and this is the current. That was our gang sign, right? All right. The pointer points in direction of field, north to south. The middle finger points in direction of current, negative to positive. And what did I have? Oh, thumb points in direction of motion. There we go. So doing that, which way will the current flow? Is it towards you? So direction of movement, north to south, north to south, direction of movement, north to south. Should be coming out then? Okay. And I'm not expecting you to memorize that left-hand rule of thumb. The only reason why I bring it up now is so you can see why something works, why this next slide is this way. And the why to this is, that shouldn't be there. Get rid of that. The why is that, well, now I wish it was there, is that this, here we go, this armature is rotating around this way. It's going that way, so it's coming back around this way. So if we can see it rotating that way, right now, if we use that left-hand rule of thumb and we figured this all out, we would see that current in this particular wire A is flowing out this way, and over here on this wire is going this way in. Does everybody follow that? It's really important that you see that. This is going this way, and that's going that way. So right now, this wire right here has got electricity going out this way and here, and it's coming all the way down, and it's going to this slip ring, out this brush, out the brush, through the load, back in and around, and it follows suit right here because that is the way it's flowing. So it's flowing that way. All right? Hope you got that. But see, this is loop A right here, and now loop A is over here. So you can see what happens. So actually we started with this one here because we had this long one on here, and we had the load going this way. But now this A wire has come around and it's over here. So now it's over here. Well, using the same gang thing here, electricity is still flowing the same way, but A, it was flowing this way in A, but now it's going this way in A. So it reversed.
So does your pointer finger always go the way that A is? Or is there, like, if there's A and B, and then when we switch to A, our fingers change the other way?
Well, yeah, because one is pointing from north to south and the direction of rotation, which way it's coming. But then if I go that way, so north to south, and it's going down, it's going to go. So it's this way, then that way. Then I'm going to fall over. Okay, so it's important that you see that. So this loop A here, it was coming out towards you, down, and out the slip ring here. Well, this A is still attached to this slip ring down here, the last one, but now it's going this way and around here. So it comes out of this top one. Before it was going in the top one, now it's coming out of. Okay, and back around. So it reversed. So for a little while, it was the load, it was going this way, now it's going this way. So it's that way, then this way, then that way, then this way. And that is called alternating current. Oh, good. What did we just learn? Nothing, so I'll skip this slide. The greatest voltage is produced as the conductor moves at right angles to the line of flux. All right, these are all supposed to be all true. Damn it, because I really thought I was going to do well finally. The left-hand rule shows us current is reversing. Doesn't matter what the left-hand rule is, just showed us. We learned it for a period of time to show us that the current is going back and forth through that particular load. So greatest voltage is the conductor moves at right angles. Doesn't do any good out here. Right angles. And, yeah, what's that?
I was rewriting right
Okay.
away. It's already on the slide.
So we've put it all together. This is what it looks like. So we start right here with this loop of wire at the right angles, moving at right angles. So if it's moving at right, yeah, no, it's parallel, not right angles, it's pretty parallel to the lines of flux, we get how much voltage? Zero. Okay, now obviously it's going to go through, a little bit more, a little bit more, a little bit more, but then we get to a point right here where the loops A and the B are actually cutting the lines. They are running, in fact, perpendicular to the lines of flux. That is the maximum amount, right? Yeah. Okay, maximum amount is right there then. So we have maximum amount. And then, of course, it's going to continue its turn until it's running parallel again. We get zero. But then as it keeps going, the loops switch sides, and that's where this came into play. Remember I said one way it's going this way, then it's going that way, then this way, then that way. Well, that's what happened here. So here we can see with my arrow that the current is flowing this way, and now we see the current is flowing that way. This way, that way, this way, that way. So what have I created here? AC. So I've got a perfectly good
AC generator.
Did I want an AC generator?
No.
No, not only that, it's not perfectly good because the faster I spin this, the higher the frequency. The slower I spin it, the... Okay, so now I've got a variable frequency single phase generator that is completely worthless to us, right? You should say yes, you do. You have a completely worthless AC generator because if I wanted an AC generator, it's no good because it can't even hold a phase, a frequency. Can't hold a frequency, so that's no good. And I'm putting it in an old vehicle that only has a DC battery, so that's no good. So what good are you? No good. Solution to the problem. I have no idea what happened there. Obviously, had a lot to write about that one, and it was probably a very important slide. All right. I don't know.
I thought it was a flat path of that 340 in San Diego.
Yeah, that's too bad. I probably tried to erase all these lines. I'm like, dang it, no, I erased whatever was good there. Okay, solution to the AC problem. We add a commutator. A commutator. And a commutator is something that is going to mechanically change AC into DC. So look what happened here is that before we had a brush here and a brush back here. And so it would go back and forth. But in this situation, we've taken the loops A and the B and we brought them to the same spot, and we gave each one of them half of a brush. So now in this case, this particular brush is always the positive brush, and this is always the negative brush. And because of the way that the loop goes, when the loop over here on the south side goes a certain way, we'll say it's always the positive one, and on the north side it's always the negative, or vice versa. So right there, you're going to pick up, well, it's on the positive, and over here it's on the negative. In a little bit, they're going to be this way and shorting out, and you're going to get nothing. And then they're going to come back around, and so this brush here, which is now negative, is going to be over here, and it's going to be positive. Do you follow that?
No,
Okay.
Can you say that again, please?
Yeah. Okay.
A little slower.
Well, I don't know if I can do that.
Maybe a little louder.
I just need it.
Yeah. So if we go back a slide, well, I'll do that. Well, 2 slides, because that one got erased. We remember that with the brush here, and each one had its own individual brush. This one would be negative sometime and then positive sometime, then negative sometime, then positive. And the same with this one. It's negative and then it's positive. So it's going back and forth. So what we're going to do is lengthen or shorten. We're going to make both of these the same length. And instead of giving them an entire slip ring, we're going to shorten it up, and each one's going to get half a slip ring. Okay? And so where one brush or one slip ring was the positive and the negative, now we're going to say whenever you're over here on the left side, you're going to be positive, and whenever it's on the right side, it's going to be negative. And so this loop is positive now, but in a little bit, it's going to go to the other side, and it's going to be negative. But that's okay, because I split it, and I put a negative brush over there, which I just made up the negative brush thing. They're the same brushes. And then that's going to pick up the negative. So this is the picking up the positive, and this is picking up the negative. There'll be a period of time where the armature is going parallel to the lines of flux and pretty much useless, but it's still going to work, sort of. And so here's another way of looking at it. This is what we had before. Just a different drawing, the magnets, and we had each one got its own individual brushes. So it created the alternating current, but now we shorten it up and we get direct current out of it. All right, this is what we get. So instead of having it swing positive, then negative, then positive and negative, we're looking at the same thing here. It's just a single loop right here. So this is the positive over on this side. This is the negative on this side. So right now,
And those stay the same.
well, I'll walk you through it. So right here we've got 0, right? So this corresponds to 0 because the loops are moving parallel to the lines of flux. But then we're going to bring it down over here. So the DC, the CD, we'll call that, or DC. I don't know why they put the A in. This one here, DC, CD, it is going up. And so if we use the left-hand rule of thumb, we would see that current is flowing this way. And the BC, it is coming back this way. So coming back this way, we'll call that the negative side, and going this way, we'll call it the positive side. So it's going to swing positive. Then it's going to continue its loop around and go negative. But now look, so the AB is on this side now, was on this side. So we can look at it and say whatever is here on the south side of the magnet is always going that, well, make it look for you guys the right way. It's always going that way. Okay, it's always going away from the slip brushes, if you will. Everything on the south side away from the slip brushes. And if it's away from the slip brushes, that makes it the positive side all the time. So everything on the south magnet is positive. Everything on the north magnet, negative. Doesn't matter if it's the AB loop or the CD loop. Follow?
Yes.
Okay. So now we just, so this time when it comes around, instead of swinging negative, well, the way we have the brushes, it's just going to pick it up again and go positive on that side. So it's going to be a pulsating positive at all times.
On, off, on,
Yeah. Little bright, little dim. Little bright, little dim.
So it's like alternating current needs stationary brushes.
So do you think,
Like it's the kind of
as it's running through the magnets, as it's rotating, it's going to require stationary brushes to keep it in the uptake converting to DC?
I wouldn't say stationary brushes. The brushes roll around with it, obviously.
Oh, okay.
They're attached and they're always spinning. So the brushes are spinning with the wire. The brushes are stationary. The
Yeah.
slip rings are rotating around. They're soldered to the wire. And the brushes stay put.
and those are what
Okay.
positive and negative.
The brushes are positive and negative.
Theoretically.
theoretically. And then the slip ring, it's like this side's positive, this side's negative. But when it rotates, this side's going to go negative and this side's going to be positive. So whatever's over here is positive, whatever over here is negative. Follow? Okay. So this is almost usable. We have no longer AC current. We just have unsteady DC current. A little high, a little low, a little high, low. Let's just figure out what the RMS is and call it a day, right?
Will it change frequency with speed as well, with RPM?
Oh yeah, it'll pulsate faster.
Okay.
If you just spin it fast enough, maybe you won't notice. It'll be like these things right here. They're pulsating so fast we can't see it. But this wouldn't really be the way to do it now, would it? But if you can understand this, you'll understand the next slide. You just add a whole bunch of loops. And then you make a whole bunch of little, instead of a half shell, you just put each one of them to a little tiny segment. And so that brush right there is touching a little tiny segment, and that brush is touching a little tiny segment. And it's only going to pick up the loop as it is kind of in the middle right there. So as soon as it starts to wander off a little bit and is starting to kind of go parallel, start at 45 degrees, we'll say, yeah, two more come in. And so it's always going to pick up the two that are the most powerful, the most usable. And you can see right there, then what you get is this little, you're going to pick it up right on the top of each wave. And so it starts to become less noticeable. So adding multiple windings and a commutator segments to the armature, the resultant output is a much better DC voltage. So there you go. Mechanically, we have done this whole thing. We don't have any solid state anything. There's no, of course, we don't have any regulators or anything. But you can see how that kind of works out. This is why I don't like PowerPoint, because I can't pace myself. But this is also why I like PowerPoint. I haven't had to write anything. I can just talk.
What was the definition that you stated for commutator?
Yeah, what's the concept?
I don't know if I gave you a definition.
You
It's,
said
there it is.
something about it transferring from.
No, a generator. A generator.
Mechanically changes AC to DC.
What he said.
Yeah, I thought you- I think it said something like
Changes
that.
mechanical energy to electrical energy. I don't think I defined a commutator.
What I
A
just
commutator mechanically changes AC to DC. There you go. That's,
That's what you want to say.
yeah. Converts AC to DC.
Thank you.
All right, what have we learned so far? Well, hey, I think I just answered that. What is a generator? Device that converts mechanical energy to electrical energy. What are the three elements needed to produce voltage?
Magnetic field, conductor, relative motion,
Magnetic field, conductor, relative motion. All right.
up and down.
All right. What is the function of the commutator and brushes?
Changes AC to DC mechanically.
To change the voltage output of the generator from AC to DC. Left-hand rule. What is each finger? Probably not going to ask you that on a test because I don't. Direction of movement, direction line of flux, and direction of current flow. All right. Oh, there's objectives for section 2. Define the term neutral plane. Explain the cause of armature reaction. Describe the effect of the. See, it always has to get rough, right? Now we got armature reaction, neutral plane, interpoles, and compensate for armature reaction. All right, let me see what I've got going right here.
Usually when you live in a different country. Yeah.
Yeah, okay, we're going to go with this one still. All right. So,
Is it neutral or neural?
neutral, N-E-U-T-R-A-L. Did I misspell something over there?
Neural plane.
Let me see. I can see that my... Where am I?
There you go.
Neutral plane, all right. Neutral plane. All right, neutral plane is the position in which no voltage is induced in the conductors. So that's the name, neutral. And that's an important point. Why do I care so much about where there's no voltage?
Because you don't want to be there.
You don't want to be there. Well, I'm dealing with commutator segments, and I'm actually dealing with a lot of amperage flowing in these windings. And every time one of these little commutator segments, they got a little spot in the middle where there's nothing, it has to switch over to the next brush. If you have a positive section of a commutator segment and a negative section of a commutator segment, and you put a brush across them, you short it out. So we got to find a safe spot to transition from one section to the other across the brushes without arcing across the brushes all the time. So you have to know where to change them. All right, so any shift of the position of the magnetic field causes a generator causes a shift in the neutral plane. So while we can look at it right now and say, well, this is really simple. The neutral plane is up there where it goes parallel to the lines of flux. The end. Next subject, please. It doesn't stay this way because what are we doing with the armature? We're rotating the armature. What's in the armature? What's the idea for armature?
Multiple windings. Multiple windings?
There's multiple windings, but let's just go back to the single wire armature. What was the whole purpose of the armature? Cutting across the flux, which created current flow. Current flow in a conductor creates electromagnetic field. Now I've got a magnet rotating inside of a magnet. Guess what that's going to do? That screws up the magnetic fields. You can't just have two magnets running around and think nothing's going to happen. So guess what happens? You get a shift in this neutral plane. So any shift in the position of the magnetic field of a generator causes a shift in the position of the neutral plane. So now you can see where these two little dots are. That should have been where the maximum current would flow because that's where it should have been cutting across. But in this, what this depicts is actually, right now, this is the armature. The armature has its own magnetic field. It's offsetting this one up and offsetting that one down. So that creates a problem. So, at first it was just so simple. It's like, well, put everything 90 degrees off. 90 degrees up, you got nothing. 90 degrees over here, you got everything. Okay, we're done. But then this comes along, you're like, well, wait a minute, everybody, back from lunch, we got a problem here. So shifts in the magnetic field are caused by change in the load of the generator as well. So if your generator doesn't need much of a load, then the shift is not so great. Get a dead battery, turn on the landing lights, nav lights, talk on the radio, do everything else, and now the draw off the generator is more, so it shifts it one way. Then decrease the load, it shifts it the other way. So you're going to have this constant shifting back and forth too if you're not careful. Well, it's by the nature of the beast. All right, this is because as current flow in the armature increases, so does the magnetic field through the armature wires. This causes a shift in the magnetic field, which is kind of what I just said. It's like I knew where I was going with this. I don't. Just as surprised as you are when I get to the slide. Now, I will tell you in very small generators, it appears that they ignore this problem. So we're talking 10, 20 amp generators. I don't see that they give much of a hoots about it. It appears that they kind of pick a happy medium and go, look it, that's a good spot there. It's not so far this way. It's not so far that way. It's going to work when it's low. It's going to work when it's high. Let's put this thing out and call it a day. And so the small generators are a lot more simplistic and they don't actually manage this issue. But the larger generators, you got to start managing it. So how are we going to fix this problem? We're going to buy an alternator, and then we'll be done.
Yes.
Okay. All right. So what do I got here? I got my neutral plane shift. Do you want me to go back? Retard the timing. Put an impulse coupling on it. That's what you're going to do. Some of you are like, crap, I don't even know what that is. Is that going to be good or bad? We good?
Yes.
Everybody good? Okay. All right, so this is just another representation of the neutral plane shift. You can see that it was going up and down here, but now it's off to the side. So as brushes cross segments of the commutator, they actually short circuit them. If you don't, the only time this is safe is when the segment is in the neutral plane. So you want it in the neutral plane when you switch commutator segments.
But the neutral plane's shifting. So
But it's shifting, so where do you put the brushes to compensate? Or do you put them on a rotating plane and figure out, so well, this is when it's 10 amps, and then when it's 20 amps, we'll move it this way, and if it's 0 amp, no, they don't do that.
it sounded like that might work.
I know, kind of would. I just made that up. I was thinking of like the old-timey vacuum advanced things for timing, we'll just do that. We'll just twist them a little bit,
Why
Or,
not just shift the plates?
so as you speed it up, we put centrifugal flyweights. As you speed it up, we'll move the whole brush assembly back and around. No.
That's the ticket.
Yeah, then you got a moving part in there.
Yeah, and then it breaks and then you lose your generator.
So how are we gonna fix that?
Now, I will confess this to you that it does seem, if you're thinking this, and you're not incorrect, that you're thinking, okay, this is the neutral plane up here, and so this is where it's safe to cross the brushes, but yet I want it over here on the brushes. It seems like that's an awful long way to go. And you would be right to think that. And I have a hard time visualizing that myself, to think, well, how am I going to pick it up here? So I'm going to swap brushes here and leave it all the way till here and then pick it back up again here. It doesn't quite work that way, but if you get this concept, it fills in. So, all right, so what happens? Well, this drawing always hurts my head a little bit. So this is what it looks like, what we're doing here. So it kind of speaks to what I was just saying. If it kind of hurts your head, this is supposed to fix it or make it worse for you. These drawings are really the same thing, but I like this one because it's represented as batteries. So here we have a positive 4, 6, 4, because this is going right angles through, and it's cutting the lines of flux the most. Decreases, then it's up here 0 where the neutral plane is. So as brush segments cross the commutator, they actually short circuit them. So right here, you can look at that. Can you see that okay? Let me see. So if we're looking at this right here, what we see is that these are the commutator segments. There's 1, 2, 3, 4, 1, 2, 3, 4. So 4 on each side. And here's the brushes. And you can see what they're showing right here is the brushes crossing this little threshold here at 0 voltage. So if I put a voltmeter between here and here, it's 0. Okay, same thing here, it's 0. But what happens as this rotates, we'll say it rotates a little bit this way, this brush is going to be on here, and this brush is going to be over, where am I going? To the left, over here. And so if we look at it, we have 4 volts here, 6 volts here, 4 volts here. Put it all together, how many volts do we have? Because they're in series with each other. So if you have in series, what do you do? Add the voltage. So over here we have 14. Over here we have 14. So we can say a positive one side and negative on the other perhaps. So 14, 14, 28. Okay, so in a second, it's going to be right here and picking it right up off of this. So if this is, we'll say this is the positive side, and this would be the negative side. And you can see how then it would add up to the two. But in just a second, it'll be riding along this. But by the time this little segment gets around and it looks like this again, this will become the 0, and this will become the 4, and this will become the 6, and this will become the 4.
So since it's in series, it'll get all the voltage.
Yes.
Okay.
Yeah, so that it's just trying to help you see why picking it up in this spot works. And now if I shift the neutral plane, then this is no longer 0. The 0 is like right here, and it's right over here. And that just doesn't work, right? I didn't even notice this right down here. It does have the negative brush and the positive brush, which is good for me. I had the right thing. This is more what it looks like because there are actual windings in there. But I like this one better because it just has a little voltage on it. So do you guys follow that so far? Okay, so we want it to cross the segments here. If it can't cross the segments here, and it's crossing it over here, then I'm short-circuiting it. So not good. So I want it over here when it crosses.
How does it cross the different ones again? So, I know you don't want to short it out, but
Because right here there's no voltage.
yeah.
So it's safe to cross. But in just a split second, this is going to rotate. So this brush is completely on this plate. And this brush is completely on this plate. And now you're going to be getting voltage.
So, but then when it gets to the next separation,
Then this one is going to spring over here and it's going to look just like this. And this one's pretty soon going to be 0. And this one's going to be 4 when it comes around. It does. But you're okay. You know, this is not something that I'm going to test you on. So if you're okay on
Wait,
this.
so the brushes and stuff stay the same.
Brushes stay the same. So this part right here, I'm not, you know, it's okay if you. So if you're kind of lost on this little thing, it's okay. You can just kind of sit back and go, that was not okay with me, but you're fine, all right? But this is one of the only things. So that and this, okay? I'm okay if you don't know those. And so brushes, segments, cross. But I want you to know why this happens, right? And so you understand.
I don't get why the 0 would shift over to the side, why all the voltages shift.
Well, the volts don't. It's just this segment right here is at 4 volts now. Second ago it was at 6, and in a second it's going to be 0.
Why?
This one right here, because it's rotating.
That blade moves here.
The whole thing is rotating, so this
Oh,
one is
okay,
4,
okay,
it's
the
going to come to
magnetic
0, then it's going to go 4,
Got
6.
it. Yeah, I thought that, like, all that stuff was like with the magnets.
So everything's turning but these two little brushes.
Got it.
Those are the only things staying put. That was helpful. Okay, so here's how we fix it. To correct for neutral plane shift, we use interpoles, also called compensated windings. Interpoles are connected in series with the armature, therefore the amount of current flowing through the interpoles is always the same as the current flowing in the armature. One thing. Yeah, okay. Just wanted to make sure I got the next note. We're going to wait for Michael to give me the thumbs up over here. Like I said, you could look for these interpoles on much larger generators. The generator that you're going to be working with in class does not have interpoles. So if you're going to look for them, you're going to be looking a long time. So don't look too hard. By the way, generators are heavy.
Yeah, they are. How heavy would you say? Like that picture, let's say.
This one right here,
Well,
by the time you get something with, oh, the little black one, that,
yeah.
what do you think, Harry? 10, 20 pounds?
No, something like that. There's just a lot. It's like solid metal. It's heavy.
Yeah,
That's crazy.
it
I
is.
could see on a 140 that originally came with that
Yeah.
generator. Oh my god.
It's like you double useful load to get rid of that. All right, interpole has the exact same polarity as the next main pole in the direction of rotation, as the next one in the direction of rotation. So I go back to this one as the next one. So here's an interpole. It's the next one. It's the same polarity as the next one, not the one it just came from. So Little south, big south. Little north, big north. Little south, big south. Little north, big north. So there's the north, north, and the south, south. This has two regular main poles, and then the interpoles that are in there. This didn't show up real well, but one of the things you kind of look for at this one, or a key point, is the fact that they were wired in parallel or series.
Series.
Series. So when you're talking generators and motors and such, you look at things that are they wired in parallel or series? And there's a reason why they do things the way they do. Whenever you run something in series, it means that whatever current ran through that thing has to run through this thing. So it's a way of keeping the interpoles at the same strength as the regular poles. Now, of course, it stands to reason that if I'm just looking at pictures of magnets, are they wired in series or parallel? Well, not applicable, because you don't wire magnets. But we're not going to use magnets, we're going to use electromagnets, and we're going to control the strength of the generator by actually making these electromagnets. So if I have current going through this one right here, then I'm going to wire it into this one, and then I'm wired into this one, then wired into that one. So whatever current flows through this one, flows through that one, flows through that one, flows through that one. So the strength of this one is going to be directly proportional to the strength of that one, which is exactly the same as the strength of this one, which is proportional to that one.
I was wondering if I could shut off the lights real quick, because I can't see any
Go
of
ahead.
those lines. You know?
Hey, you're the one sitting by the lights. You do whatever you want. You see me running back that way, turn it back on.
Top one a bit better.
Yeah.
On
Top
these
one,
you
yeah, the top.
Yeah, I told you, it's not a big deal. It's just like this has one wire coming out here, and then it's got kind of the I don't know, lines of flux going that way and one wire, and then you have three wires coming out of this one and three coming out of that one, and heavier here, which is more or less what I just explained to you, that they're wired in series so that you always have the same amount of current traveling through all of them, and that's how you do it. So if the current through the main poles gets stronger, it is going to throw out the interpoles, or throw out the neutral plane. Then you just run the same current through your interpoles and they'll compensate. So the stronger the magnets are north, south here, electromagnets, the stronger your interpoles are going to be. It's so simple. All right, I guess I'm done with that. Yeah,
So that's why the neutral has been shifted now, is because we have the interpoles in there? 'Cause-
the interpoles are keeping it. And so if I need more electricity and I tell the generator I need more, because you have to think about, we're going to get into this, is a generator just doesn't run, it's got to have somebody tell it what to do, right? And so you have a box that tells it what to do. It says, hey, we need more electricity. Well, how are you going to get the generator to do it? Can't spin it faster, it's tied to the engine. So what you're going to do is you're going to increase your electromagnets. You can make stronger magnets. So these are not permanent magnets, they're electromagnets. So there's going to be wires wrapped around here, and so you send more current to the generator and it will make more current. Pull off some current, it'll make less current itself. So, yay. Okay, now we can go to writing notes.
Yay.
What was I doing?
What, is that a sarcastic yay, or? Well, I wasn't, so. All right, so we're talking about generators. Black. There. So I had one. So generator. Generators. And point A is PowerPoint. So everything we just talked about was A. B. Like that?
Yeah,
That's everything I'm going to talk about.
write that down.
All right. So as we see, yeah, it just took me all day to do it. As we see, or can see, DC, which stands for,
Direct current.
all right, generator. Generator will ultimately produce,
AC.
ultimately, the end product,
Oh, DC.
okay, rippled DC. It's not perfect, it's got little ripples to it, and the more armatures that you put in there, and the more commutator segments, the smoother it's going to get. So we'll produce rippled DC. All right, how can we fix some of that?
Commutator.
Well, the commutator is how we got the DC to begin with.
Yeah.
So with the use of a capacitor, capacitor, right, stores electricity, acts as a filter. Okay, we can filter out. We can filter out some of the ripple. That's a good thing. All right, and point C. This is probably a good thing to write before we leave. In our example, which is everything we just covered in that PowerPoint, which, by the way, I believe is in Canvas, for those of you taking photos of it. If it's not, somebody let me know. In our example, where am I? We used a rotating armature. Correct? And that is correct. A rotating armature and permanent magnets. We never talked much about current flow. I mean, just till the end I mentioned it. And we used armature and permanent magnets. In an actual generator, this will be my last sentence. In our actual generator, or in an actual generator, that makes more sense. An actual generator uses, I like that better, it uses electromagnets. Electromagnets wrapped around an iron core. And that's where we'll end it.